Section: Introduction. In this section, we introduce the concept of planning, which involves strategically searching for the best action sequences to achieve our goals from initial states. This has been a key aspect of artificial intelligence since its beginning, leading to significant advancements, such as superhuman performance in games like Go. Recent developments show that combining large language models, LLMs, with advanced planning algorithms greatly improves performance on complex reasoning tasks, moving beyond traditional chain-of-thought methods. A notable example of this is OpenAI's work. These advancements allow LLMs to efficiently explore various potential solutions, resulting in more accurate outcomes. Additionally, there is growing interest in creating generalist web agents that can plan and execute actions to complete complex tasks across different websites. This interest stems from the web's potential as a realistic environment for agent research and development. However, applying existing planning algorithms in the online web environment poses significant challenges, particularly concerning safety risks. For instance, there is a danger of unintentionally submitting sensitive information or triggering unwanted transactions during live interactions. These risks are heightened when using exhaustive tree search algorithms, which can expose agents to hidden vulnerabilities and unexpected situations. Moreover, many online actions, like confirming a purchase or sending an email, cannot be undone, making backtracking, a vital part of planning, very difficult. One promising approach to tackle these challenges is model-based planning. This method allows agents to simulate interactions using a model that represents the dynamics of the environment. By simulating action sequences in a virtual setting, agents can safely explore potential outcomes without directly engaging with live websites. This not only minimizes safety risks but also maintains the agent's ability to plan and explore. The main challenge, however, is developing a versatile model that accurately reflects the constantly changing landscape of the Internet. While previous studies have shown that LLMs can serve as effective models in simpler environments, we pose a more ambitious question: can LLMs effectively model the vast and dynamic Internet? Given their extensive pre-trained knowledge of web structures, protocols, and user behaviors, LLMs are well suited for this task. Building on these insights, we present WEBDREAMER, an innovative framework that utilizes LLMs as models to navigate the web. Central to WEBDREAMER is the idea of dreaming. Before taking any action, the agent uses the LLM to envision the outcome of each possible step, described in natural language. These simulated outcomes are then assessed based on their progress toward the task objective. The most promising action is executed, and this process is repeated until the LLM determines that the goal has been achieved. To test the effectiveness of WEBDREAMER, we evaluate it on two benchmarks that support online interaction: Visual Web Arena and Mind2 Web Live. WEBDREAMER shows significant performance improvements over existing agents on both benchmarks, highlighting its practical value despite its conceptual simplicity. While tree search methods with actual interactions perform slightly better in the controlled environment of Visual Web Arena, they are often impractical due to safety risks and the potential for irreversible actions on real websites. In contrast, our simulation-based approach provides a more flexible solution, balancing performance with practical applicability in real web navigation tasks. In summary, our work opens a new avenue for AI planning in complex real-world environments like the web, using models simulated by LLMs. With WEBDREAMER, we address the dual challenges of safety and complexity in web navigation. Our results demonstrate the potential of LLM-based models for planning in intricate web environments and highlight new opportunities for optimizing LLMs as models and enhancing model-based planning algorithms for language agents. In the following sections, we will discuss related work, including advancements in web agents, which aim to automate tedious web tasks using multimodal language models. Benchmarks have evolved to provide increasingly realistic website simulations, challenging models to handle visual information and generalize across various tasks and domains. We will also explore world models, which are essential in model-based reinforcement learning, and how LLMs can facilitate decision-making and planning rather than just training. Our study aims to push the boundaries of LLM-based models in more complex real-world environments, particularly diverse websites. Section Summary. In this section, we introduce WEBDREAMER, a framework that utilizes large language models, LLMs, to simulate web interactions, allowing agents to safely explore potential outcomes before executing actions. Our approach addresses safety challenges in online environments while demonstrating significant performance improvements in web navigation tasks compared to traditional methods. Section Preliminary. In this section, we discuss the task formulation for web agents that automate activities on live websites. We frame each task, guided by instructions, as a partially observable Markov decision process, or POMDP. Here, we define the environment's possible states, the actions the agent can take, the observations it can make, the state transition function, a reward system indicating task completion, and a function that maps states to observations. Our goal is to perform a series of actions that yield a reward of 1. However, due to the complexity of web environments, we can only observe a limited view of the true state, which includes server variables, dynamic content, and hidden elements. This limited observability shapes our action space, which consists of actions like clicking elements, entering text, and navigating URLs. Next, we address the challenge of planning optimal action sequences. Directly planning through real interactions is costly and can lead to irreversible actions. Instead, we use model-based planning, which allows us to simulate interactions using a computational model of the environment. This approach helps us predict state transitions without executing actions in the real world. While offline planning can work in simpler environments, web environments require online planning, where we compute one action at a time. A key method we use is Model Predictive Control, MPC, which simulates future actions and selects the best one based on predicted outcomes. Since we cannot access the real state due to partial observability, we simulate using our observations. We introduce WEBDREAMER, a novel approach that utilizes large language models, LLMs, for efficient planning in complex digital environments. We believe that web interfaces, despite their complexity, are designed to be predictable for users. Humans can often anticipate the outcomes of their actions based on visual cues and common design patterns. Given that LLMs are trained on extensive web data, we think they can effectively simulate the consequences of user actions. WEBDREAMER follows the planning through simulation paradigm. We simulate two-step trajectories for candidate actions, select the best one, and execute the corresponding initial action. The LLM serves as both the simulation and scoring function. For simulation, we have two modules. One predicts state changes after an action, and the other imagines the next action based on the predicted state. This generates trajectories of a configurable length. For scoring, we evaluate each simulated trajectory on a scale of complete, on track, or incorrect, and average these scores. To generate candidate actions, we use a two-stage approach, first sampling the top actions and then refining them with the LLM to eliminate unnecessary ones. This refinement is crucial as the relevance of actions can vary at different steps. We also include a termination check to ensure the model stops under certain conditions. All system prompts used in WEBDREAMER are detailed in the appendix. Section Summary. In this section, we outline the task formulation for web agents as a partially observable Markov decision process, POMDP, and introduce WEBDREAMER, a model-based planning approach that utilizes large language models, LLMs, to simulate action outcomes and efficiently plan in complex web environments. Our method involves generating and scoring action trajectories to adaptively select the most promising actions while navigating the challenges of partial observability inherent in web interactions. Section Discussion. In this section, we discuss our testing setup for evaluating the real performance of our planning framework. We utilize benchmarks that allow for online evaluation to reflect the dynamic nature of web interactions. Our focus is on two key benchmarks: Visual Web Arena, VWA, which emphasizes a multimodal approach, and Mind2 Web Live, which primarily uses HTML. VWA consists of 910 tasks across 3 websites: Shopping, Classifieds, and Reddit, while Mind2 Web Live includes 104 tasks from 69 real websites. We stick to the default settings for both benchmarks, using screenshots with set of marks prompting for VWA and HTML for Mind2 Web Live. We select the most advanced multimodal LLM available to help us explore model-based planning with LLMs. In our experiments, we set the planning horizon to 1, with a detailed analysis of this parameter provided in a later section. To showcase the effectiveness of our approach, we compare it with 2 main baselines: the interactive agent and the tree search agent with real interactions. We can implement our method for both benchmarks, but we can only compare with the tree search baseline on VWA due to the challenges of applying tree search in real websites in Mind2 Web Live. In VWA, the agent tracks action sequences to reach previous states and can reset the environment to restore those states. However, this reset is not always possible in the real websites of Mind2 Web Live. Our model-based planning approach relies on 2 key aspects: state representation and planning horizon. To understand its effectiveness and limitations, we analyze how different configurations impact performance. Given the high computational cost, we use a subset of the VWA dataset with 100 shopping tasks and human annotated trajectories. We explore various state representations, including predicting HTML code or the accessibility tree of the resulting web page, and evaluate planning horizons of 1, 2, and 3 steps. Our findings show that all 3 state representations outperform the interactive baseline, but their effectiveness decreases as the planning horizon extends to 3 steps. This suggests a common issue with long horizon simulations, where the proposed actions may not exist in the predicted state. The state change representation shows the most significant performance drop, especially at a planning horizon of 3, as it relies on the model inferring available interactive elements. In contrast, HTML and accessibility tree representations provide clearer information, making them less prone to errors during longer simulations. Despite its limitations, the state change approach remains a viable option, matching the performance of the other representations for shorter planning horizons while using fewer output tokens. To assess whether the improvements we observed stem from specific components of our model-based planning approach, we conduct ablation studies focusing on the simulation and self-refinement stages. We pay particular attention to the simulation stage, which is central to our planning method. We test the idea that improvements might come from simply re-ranking candidate actions without simulation. By removing the simulation stage and having the reward model evaluate candidate actions directly, we find some improvement over the interactive baseline, but it is minimal and still lags behind WEBDREAMER. This confirms the importance of LLM-based model simulation in our planning process. We also notice a drop in performance when the self-refinement stage is removed, primarily because this module effectively filters out less relevant actions when the next optimal action is clear. In contrast, simulating all actions directly can introduce noise that negatively affects performance. To illustrate the role of simulation in planning, we present a case study with both positive and negative examples. This highlights how simulation helps the agent explore the environment and how inaccuracies can lead to incorrect predictions, with detailed examples available in the appendix.